I'm going to talk about the temporal difference learning algorithm. Our goal is to replicate the result of two experiments done in Sutton's paper. We would like to apply temporal difference learning on a bounded random walk problem. Here we have a system of 7 states and it starts on the middle state D and it can move in both directions with equal probability on intermediate states until it reaches either to the state A or G. If we reach the state G, then we observe 1 or 0 otherwise. Our goal is to predict the probability of ending at G on a given intermediate states. For this problem, we would like to use temporal difference learning algorithm. In TD algorithm, the update equation is given like this, and it incrementally updates W by taking temporal difference in predictions. Here, lambda takes values between 0 and 1, and this TD can be taught as generalization of Midterm procedure for lambda equals to 1. This update rule is implemented in algorithm 2 in an efficient way. For the first experiment, the W parameter is not updated during the processing on sequences. Instead, the increments are accumulated and added to the W at the end of the whole training set. Therefore, we pass the same training set several times, and this is called repeated representation. The learning procedure stops until there is no significant variation in W between iterations. In the second experiment, we just update the parameter after each sequence and the training set is passed to the algorithm just once. Here's the setting we use during the experiments. We have 100 training sets with each of 10 sequences. We perform 2 experiments and the lambda and alpha take values between these 2 sets, and for each execution we associate it with an RMS value which is computed as follows, and here P is the true probability distribution. As we can see, we successfully generate the same pattern for the first experiment. TD lambda outperforms Midterm procedure. The smallest RMS value is achieved for lambda equals to 0. In the second experiment, we try to investigate the effect of learning rate parameter on the performance. For a given lambda, the algorithm was run for different alpha values and the RMS values were plotted for those executions. Again, we successfully generate the same pattern in the figures. Performance of our algorithm is consistent with figure 4 in Sutton's paper for alpha between 0 and 0.45. This is the last figure, and again it is consistent with the figure 5 in Sutton's paper. We see a convex function relationship between lambda and RMS value. The TD lambda algorithm achieves the best RMS at 0.2, whereas the best performance was achieved in Sutton's paper at 0.3. In summary, we successfully replicated the performance pattern in the result of Sutton's paper with slight difference in RMS values. This is probably using different training data sets and limited amount of data. Thank you so much.